Hello, my name is Lloyd, and welcome to my research paper presentation on space travel and planetary sciences. My research topic centered around an investigation into the considerations and challenges for exoplanetary colonization and space travel. In this presentation, and in my paper, I discussed the star system considerations, the factors for choosing a habitable planet, why you want to colonize an uninhabitable planet or other stellar bodies, as well as considering the logistics of interplanetary travel and beyond. When it comes to looking for inhabitable star systems, the best candidates are red or orange dwarf stars, classified as M or K-type main sequence stars. These are characterized by having a less intense surface temperature, being smaller than our Sun, and having a very long main sequence life, and are generally quite stable. Their main sequence life can range anywhere from tens to hundreds of billions of years, so they live a lot longer than our Sun does. Due to their long main sequence life, they have a higher likelihood of harboring life, or even evolved life on their own. As humans have evolved around a G-type star about 4 billion years in, it is possible that life has also grown around a red or orange dwarf star given their longer lifespan. The most important factor for selecting a location for a suitable human colony are habitable planets. Habitable planets are thought to exist typically in an area around a star called the habitable zone, otherwise known as the Goldilocks zone. This is an area that is neither too hot or cold for liquid water to exist on its surface. In the context of human colonization, there are also some other features that we should discuss. The first is temperature. While humans can exist in dangerous conditions for some amount of time, their core body temperature is what matters most in most cases. Anything higher or lower than around 39 to 35 degrees Celsius can eventually cause lasting damage and perhaps be fatal, so it's important to maintain that temperature range. The second is water. Waters require a minimum of 2.5 to 3 liters per day, but can also increase up to 7.5 to 15 liters per day for survival requirements. An ideal planet should provide for this requirement as water is difficult to transport from off-planet, and it's logistically challenging, but this can also be augmented by using atmospheric water generators. The third is energy. Energy can be derived from three main methods. The first is solar energy, which is taking the energy provided by a star. The second is geothermal, which is taking the energy from the heat radiated from a planetary core, or tidal forces, which are just the pulling and stretching forces provided by a planet's satellite or a moon. This is important for day-to-day regular use and for survival, such as running water generators, heaters, coolers, and so forth. However, it's a bit difficult for humans to currently apply the forces provided by tidal energy. The fourth feature that should be discussed is radiation. In most cases, with habitable planets, hopefully the planet should have a thick enough atmosphere or magnetic field that can remove the worst of the radiation. So depending on how habitable a planet is, also technically applies to its atmospheric composition in terms of mitigating the effects of radiation. Alternatively, if there is not a strong magnetic field or a lack of thick atmosphere, radiation shielding materials are just as important, as well as minimizing exposure to the sun, or a star, sorry. The final is an atmospheric composition. Ideally, obviously we would want a composition similar to Earth, which is approximately 79% nitrogen and 20% oxygen, around that mix. However, higher levels of oxygen are also possible and are not technically lethal depending on pressure differences. While uninhabitable planets and other bodies are more difficult to colonize due to the fulfilling less requirements to sustain a human presence, it might still be worth the cost in order to attempt to inhabit or at least maintain a presence nearby, on or near them. The first reason would be resource exploitation. Stellar bodies like asteroids have untold amounts of raw resources that would be very beneficial to mine. In terms of scale, it would be less logistically intense to set up a facility to mine an asteroid than a mine on a planet. Asteroids are also extremely dense and useful materials for industrial purposes. For example, according to Asteroid, the asteroid Ryugu has potentially $82 billion worth of resources such as nickel, iron, cobalt, and water inside of it. It also is easier to transport a mine to a destination just because of its low gravity or zero gravity environment. A second is researched. Uninhabitable planets may possess features that may or may not be found on habitable planets, which could be a boon for science. A specific example of this is Enceladus. It's thought that Enceladus may harbor life under its ice shell, which would provide a fascinating perspective on how life evolved on a stellar body outside of what we experienced on Earth. Finally, the third reason is just simply interplanetary logistics. Having a space station on a Lagrange point enables space travelers to a well-documented and easily accessible location to rest and refuel along their voyage. Also, being located in a zero gravity environment makes it easier to access than orbiting a planet or landing on the ground of a planet. Another factor to consider when colonizing a planet is how you're actually going to get there, and that is through interplanetary or interstellar travel. There are a few things to discuss in this field, the first being propulsion mechanisms. It's difficult to say what will be the most feasible transportation method, as current means are inefficient time-wise. For example, the Voyager 1 is the farthest man has ever gone into space. It's been on mission for 44 years, but it's only barely broken out the heliosphere out of the sun's influence. The next is genetic makeup. In order to ensure that successive generations don't degenerate genetically, we need to ensure a minimum of at least 50 to 100 individuals to ensure that the gene base is diverse enough to prevent a genetic downward spiral or to prevent any inbreeding issues. Food and water production is also another problem. Microgravity does affect how plants grow, and successive generations are affected by microgravity in that sense. Water, however, can be a bit more easy to acquire depending on how you look at it. For example, water can be recycled from wastewater and urine, as is the case on the ISS, but can also be extracted from asteroids or comets. Physical health is also a large factor in determining the logistics of travel. One major category is muscle atrophy. Muscle atrophy is very important as a lack of exercise and microgravity causes the muscles in the human's body to slowly waste away just due to less exertion on muscles, primarily in the legs. Another problem is radiation. Radiation can be prevented by some plating, but doesn't stop things like cosmic rays. You would need something like a magnetic field to mitigate the worst of those cosmic radiations. Finally, there is the issue of mental health. Mental health is interesting because it is an unbelievable strain on what most humans would consider their psyche. In order to mitigate this could be done by creating engaging environments and a schedule to ensure that the mental health of a space vessel's occupants are well maintained. This can be done through things such as gardening, interpersonal communication with family and friends at a planet or home, entertainment, maintaining a consistent sleep schedule, and so forth. In summary, we looked at stars that are suitable for colonization, what some characteristics of a habitable planet might look like, some reasons why you would want to maintain a presence around uninhabitable stellar bodies such as asteroids, as well as some considerations for what humans would need to prepare for when it comes to interplanetary travel. Okay, and that is all. Thank you very much for your time and watching my presentation.